In this video, we will talk about what 1 plus 2 plus 3 plus dot 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 up until n is, and some other summations like this and what their formulas are. So my goal is to find a closed formula for this sum. So we introduced sigma notation in the last video, but the way I read this is take this value at the bottom, I equals 1, and plug that into the formula for our sequence. Plug that into I. So if I plug in 1 for I get 1. Then plug in the next integer up, which is 2, which would give me 2. Then the next integer up, which is 3, and start to add these together. So plus here, keep going until you reach the integer written at the top. So that's n. So what I want is I want a nice formula for what this whole thing equals, rather than having to just put plus dot 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 dot. That gives me a really quick way to add these terms together. So there's a really nice proof of this, and I want to show that. So I'm going to begin by letting this sum I'm trying to compute be called s. And what I'm going to do now is write s one more time, but with the terms reversed. So I'll put n first, and then I'll put n minus 1. And then the thing before that would have been n minus 2, and keep going like that until you get to the end. So the last two terms in this series would be 2 and then 1, if I'm going in the reversed order. And what I notice about this now is, if I look at each pair that's right above each other, or underneath each other, so this first pair, this second pair, the third pair, all of the pairs add up to the same value. Like they add up to just n plus 1, all the way down to the n. So I'm going to take advantage of this fact and add these together. So s plus s on the left is 2s. On the right, each of those parentheses become n plus 1. So the first circle thing is n plus 1. The second circle thing is n plus 1. All the way down to this last one is also n plus 1. But how many of these pairs are there that we circled together? Well, this numbering started at 1, and it went all the way down to n. So there are n of them. So there are n of these parentheses. Okay, so I get 2s equals, so if I add the same number to itself n times, well, that's just n times n plus 1. All right, so now I'm one step away from figuring out what s is. I just divide the 2, and I get s equals n times n plus 1 over 2. And we got it. That is our formula for what this sum of the first n positive integers is. Just as a check, let's test it out for a small value. Let's test it out for like n equals 5. If I plug 5 into this, and I actually do 1 plus 2 plus 3 plus 4 plus 5, well, if I work this out, it equals 15. But let's show that if I plug it into the other side, I get the same thing. On the other side, what I would get is 5 times 5 plus 1 over 2. So this is 30 over 2. But that's 15. Those are equal. Those are equal, and I like that. So why this formula is really nice is, well, this works for any value of n. So if I needed to add the first 1,000 positive integers together, I could just plug it into here, plug it into the formula, and get the answer really quickly. Okay. All right. So there are a number of nice summation formulas like this. So for example, the second summation formula I have in the list is, well, what if I wanted to sum like 1 squared plus 2 squared plus, and if I keep going like that up until plug in n, up until n squared, it turns out that equals a slightly more complicated looking thing. I could also sum the first n perfect cubes like this, and there's a formula for that. I won't prove those in this video, but they are provable. They are provable. We can prove these using a technique, induction, which we'll actually see later in our class in chapter 5. Okay. There's another formula for if I have a sum of two sequences either added or subtracted together, I'm allowed to sort of distribute the sigma to each part and do the sum of the first sequence, and then either plus or minus, depending on what this sign was, and then the second sequence's sum. if there's a constant k multiplying my sequence, we can pull that out in front of the sigma. That's what this property says. Okay. There's one more of these, which we can actually give a proof for. That's simpler than the one that we just did. This thing right here, so I'm going to start off by plugging in 1 for this, but there's no I to plug into, which means if I plug it in, I just get 1. Then if I plug in 2, again, there's nothing to plug in for, so I just get 1. If I plug in 3, again, I just get 1 because there's nothing to plug in for. And if I keep going like that, I get plus dot 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 up until 1 again. Because even when I plug in n, I still just get 1. So how many times are we adding this together? Well, I started off plugging in 1 and ended up by plugging in n. So we are doing this n times. So if I add 1 to itself n times, well, that just equals n. Okay. So nice. So let's do a practice problem where we use some of these summation formulas. Let's say I want to find a closed formula for the sum from 1 to n of 2i plus 5c. So let's use some of these properties. Okay, so what I'm going to do first is, I notice I'm adding two sequences together. So I can use property 5, which says, well, this becomes the sum from I equals 1 to n of 2i plus the sum from I equals 1 to n of 5c. Let me also just mention that here, well, I is this variable that I'm plugging in for. So the c is some constant. It's some real number. Okay. So what I want to do now that we've gotten it started together is give you a chance to try this and see if you can continue it. So pause the video for about 2 minutes and see if you can keep this going and use some of these summation formulas to get a closed formula for this. So pause it in 4, 3, 2, 1. Pause it and try this. All right, so hopefully you did that. Hopefully you paused it and you tried it. So in both of these, we have a constant inside of my sum. So let's pull that constant out. So I can pull the 2 out times the sum from I equals 1 to n of I. Let's write the I better, of I. And the next one, I also have the constant 5c. That whole thing is a constant. So I can get 5c pulled out times the sum from I equals 1 to n. And we'll be left with just 1 inside the sigma. Oh, but now I have a couple of the formulas that I needed. So the sum of I, well, that's this one up here. The other one that I see is the sum of just 1 a bunch of times. And that was this. So I can plug in the formulas that we got for those. So we get 2 times, and then plugging in for this sum, 2 times n plus 1 over 2. And then I get plus 5c times that next sum, which ended up just equaling n. I can cancel these 2's. So that leaves me with n times n plus 1 plus 5cn. And that is a closed formula. Got a closed formula. It didn't say I have to simplify it further once I get a closed formula. So it's fine to leave it like this.